in sizing, right? You guys don't want to get involved so much in the sizing. However, if you get involved in the controls part of it, and I was talking with Seth after school on Tuesday, one of the things that sort of enhances your ability to be a good service technician is sort of knowing the bigger picture, right? There's stuff that you're responsible for, but there's stuff that you may not be responsible for, but could potentially assist in solving the problems. And one of the things is you got a air handling unit that's maybe not so good on controlling, right? Like maybe at certain positions, it's like not maintaining temperature or something like that. One of the things that can happen with that, if it's a waterside system, is that the valve is oversized, right? So one of the things about maybe getting it right for your customer or making sure that things are working right is have some knowledge of this waterside control stuff and what are the implications of like not putting the right valve in there, okay? Again, you guys aren't responsible for it. That's a design engineer's responsibility or a design build engineer's responsibility, but I want to give you guys just some insight on that, okay? So what we're going to do, I'm not going to spend, maybe I'll just touch on here briefly. We're going to go through sizing pressure-dependent valves, which is the biggest, I guess, hassle of this. And sizing pressure-independent valves, it's easy. You just pick it on the flow rate, all right? But this pressure-dependent stuff, it's the large majority of the valves that we deal with, and this is where we have the problems, okay? So I'm going to try to give you guys a little bit of insight on it. This is going to be like sort of level 2 stuff. And if you're inclined to want to increase your knowledge in HVAC, I encourage you to pay attention here because the pressure-independent valves are coming, and they're coming maybe sooner than you think as far as the way it's happening in the industry. We've had a long lead time, like probably back 2003, pressure-independent valves entered the commercial market. And what's it now, 2017? It's just starting to get the momentum, and I'll give you some insight on that. Again, I'm not going to spend so much time on Belimo's nomenclature. You guys all have the catalog, and I'm not going to beat that to death. You know, you guys know how to read and look up stuff. That's more of the salesy stuff. What I'm going to try to give you guys today, and I'm going to try to give you guys for all the different valves that we're doing, I'm going to try to give you what we call like the application knowledge. For instance, here's a really good example. A globe valve. Does everybody know what I mean by a globe valve? Anybody not know what I mean by a globe valve? Okay. The globe valve, I'll show you one a little bit later on. It's a valve where it's sort of like the body of it has sort of like a cylindrical, like a spherical thing in the middle, so it looks like a globe, right? It's an old-fashioned term. That's different than a ball valve, right? So a globe valve typically has an action of a linear actuator that goes up and down. That's a globe valve. A ball valve is a rotary valve where you turn it like 90 degrees typically, and you open and close it that way. Globe valves are expensive. They spend a lot of money to cast, right? They're expensive pound for pound. You don't want to use a globe valve. If you're just going to do 2-position control, just shut water on and turn water on, don't spend the money on a globe valve. What would you use? Like if you had say you had like a 4 or 5 inch pipe and you needed just a valve for doing 2-position control, what do you think you'd choose?
Butterfly.
Yeah, butterfly, right? They're inexpensive for the most part, right? The channel ones are. And that's all you want to do is just get the water on and off. However, if you want to control a coil, right, and control, fairly closely on temperature or on flow, then you use a globe valve, right? Because you're going to pay the money for a little bit better control, and we'll explain to you what that means in terms of what kind of valve it should be and the application that we have for that. So that's the kind of stuff I want to go through this afternoon. Not all of this is in the book, okay? So if you're inclined to want to remember it, however you want to write it down or whatever, I am going to give you guys my card by the end of tonight. So I'd encourage you, if something gels in the field where you say, yeah, that guy was talking about something that's similar to this, feel free to call me, because that's where I want to get. All right, so let's get into it. So this is sort of more, I guess this is a little bit minutiae. I'm trying to go this fairly fast. Most of you guys know this. So we need control valves when we're doing like new construction. How many installers? Do we have new construction installers here? Guys didn't install control valves? Are you guys not valve? Not valve, just electrical install? So we don't have any fitters that are. The fitters do all the installation of control valves. So this is pretty common sense, right? New construction or replacement. Now there's another term, right, that we use. There's new construction, which is new stuff. There's replacement. What's that other word that starts with R. Retrofit. So what does retrofit mean, you think? Well, what it means is, and this is what I'm going to define it as, if you say replacement to me, I mean you want to replace that whole control valve assembly, which means what? The body and the actuator. That's replacement. Retrofit would be either replacing the valve body, not so common, or more commonly what? The actuator, right? That's when I say retrofit, that's what I mean. Okay, in terms of valves, okay? And we'll go through the retrofit section in the catalog, and that's probably where you guys can probably have the most, say more of the more practical stuff. And as I don't know if I mentioned this, I did mention about damper sizing. We have a retrofit app you can put on your phone. All this stuff is available to you on your phone, as far as the sizing stuff and selection stuff and looking for cross references for damper actuators and control valves. This stuff is all available on your phone. All right. So bear with me on this. This particular slide is sort of our guideline for the next couple of minutes. We're going to talk about the things that you got to consider when you're doing a valve selection. So it includes not only sizing, but also selecting what kind of valve do I want, or the type of thing crosses that I'm going to control. All right, so hang on. Again, not much in the workbook on this. Some of this is common sense. Okay, media types. When I say media, I mean like what we call is working fluid, right? That's the technical term. So either we got HVAC water, right? Chilled water, hot water. What's glycol really, right? Glycol is water, right? It just has propylene glycol in it, okay? So we got water and we got steam. We're not talking about steam. I'm sorry? You have a question? Okay. Steam we're not going to talk about today. This is sort of an entry-level course. We're not going to get into steam valve sizing. If you guys are interested in that kind of stuff, we can talk about that another day. So the design data. Here's where we're going to get into sort of what I call the egghead stuff, and that's the engineering stuff. Okay. So when you select a pressure-dependent valve, you got to deal with this thing called a CV. Anybody heard that term before? Nobody? Okay, so the CV, think of it like this. The CV is the amount of water that goes through that valve when it's fully open for a given pressure drop, right? You have to drop pressure across that valve in order to control the flow. This CV is going to sort of give you an indication of how much water you're going to get through that valve at a certain pressure drop. The definition is the amount of water through a fully open valve at a 1 psi drop. That's just the math. But I mean, you're going to select that CV based on what you're going to try to go for a target. You can try to select that valve based on that CV. So if you select a CV that's too high, what I mean is you calculate what you think you need, but you select a valve that's got a much larger CV. What happens here is that you oversize the valve. So let's just think about it. I just want to give you guys, if you oversize a valve, and I know you guys aren't control experts, but you deal with controls in some regard. If you oversize a valve, what do you think the implications would be of oversizing a valve in terms of the control?
Overshoot, undershoot.
Say again?
Overshoot and undershoot.
Well, it's sort of like it's going to oscillate. It's going to be unstable, right? I mean, that actuator is going to be working hard. So here's what happens, really. You size the valve at a certain CV, okay? Well, if it's at that flow rate and it's fully open, it's probably going to be fairly cool, right? But as you start to get that throttle down lower and lower in your range, it wasn't selected at that position, right? It's going to tend to be oversized and it's going to start to oscillate. Like you said, it's going to sort of like, if you looked at the actuator output, it would sort of be like this. Now, it might be controlling. Oh, more pizza? Jeez.
Sorry, dessert pizza.
Oh, it's dessert pizza? Okay.
Pizza. They forgot it.
All right. So in terms of control valve things, if you oversize it, you're going to sort of have unstable control at the low end. That's one effect. Okay. Now, if you undersize it, what's the implications of that?
Moving up water.
Well, yeah, they talk about starving the coil. What the real implication is, if you undersize valves, you're going to take a higher pressure drop across that valve, and you may get to a point where the pump can't handle it, right? The pump may not have enough head to be able to push the water through that valve under certain conditions. So you could have like I say, a low flow condition, and that's not good either. So the whole key here with pressure dependent valves is to try to understand, what the pressure drop should be based on where it's in the system, and then pick it as close as you can to that. So here's the magic formula. We sort of simplify it for HVAC. If you're interested in this formula, you guys won't use it a lot, but actually it's in your workbook and it's on page 26. So what this means is you take the design flow rate in GPM of the coil, and then you divide it by the square root of the pressure drop that's across that valve when it's fully open. All right, so we know what delta P is, right? If you had a manometer, you could go across that valve and you could measure the difference in pressure when the valve is fully open. We don't always do that, but that's actually what we call the delta P, right? P1 minus P2. Okay. Now, if we're going to do we're going to do just an example to show you how this works. We're not going to get all wrapped up in the math, but I want to show you how it works. So, the first thing you got to know is you got to know these two things right here. You need to know the flow rate, the design flow rate, whatever that coil is supposed to be doing, right, in maximum flow. And then you got to figure out what this pressure drop is if somebody doesn't already give it to you. So in this case, what we're going to do is we're going to start out, we're going to say we've got a 40 GPM coil. That means, now where would you find that information, the GPM, if you're doing this?
Prints.
Yeah, be on the schedule, right? Yeah, be on the prints. Hopefully you got record drawings down the basement while the bodies are buried or something. You're going to have something that tells you this is what the flow rate is. Now, these other two things is like, okay, delta P and CD. Well, here's the rule of thumb. And if you did it this way, if somebody put a gun to your head and said, you need to size that valve, if you did this, if you said you picked a value between 3 and 5 psi to size the valve, you would be on solid ground. That is to say, most people would not disagree with that. And, in engineering, we call it standard of care. There's a lot of engineers that put this right in their specifications. They say, look, we want you to size these valves between 3 and 5 psi. Now, it is a little bit sort of a little bit out of the rear end type of situation, but it comes from years and years of people saying, well, this should be the way it is. But I can give you a little bit of insight. It ain't necessarily so, but this is where we start. Okay. Now, if you're looking at that range right there, and you had to pick a value between in that range, what value do you think you picked? 4. Yeah, that's right. Two reasons for that, right? One, it's in the middle of the range, right? I guess from the engineering side, we like picking things in the middle of the range, right? We say, okay, we're just gonna hit the mean value. We're gonna pick 4. What's the other reason?
Even number.
The math gets really easy, right? It's an even number, but the math gets easy, right? Because what's the square root of 4? 2, right? So you can do that one in a truck, right? You can be driving down the road, and the guy says, I got a 150 GPM valve. What's the CV? 75, right? I mean, you're a genius, right? So no, but really, that's the way these valves are picked. I mean, it's not this mystifying, Buddha stuff. A lot of valves get sized this way. Now, I'm not saying it's absolutely right, but it is done, and a lot of people do it. All right, so let's do it. We got a 40 GPM. We got a pressure drop of 4 psi. What's the CV?
20.
20, right? Easy. No problem, right? I'm not going to go through these. These are just calculations to show you. And we know, right? 17 divided by 2 would be 8.5, right? 40 divided by 2 would be 20. This one's not as easy to do, right? Because the square root of 3 is not even, right? It's like 1.73 or something like that. Okay. All right. What's that?
Electricians have that.
Yeah, that's
Well, right. That's right. If you got 3-phase, that's right. You got 3-phase power, you got to know the square root of 3. That's right. All right. So here's what we've done so far. We talked about media. We talked about this pressure-dependent valve sizing, and pressure-dependent valves focus on this thing called CD. Okay. Well, pressure-independent valves. Okay. Has anybody heard this term before? Probably not. Okay. Well, like I said, they're coming. They've started out a long time ago. think about it this way. Now, you guys probably haven't thought about this, but I'm trying to expand your horizons a little bit today. VAV boxes, you know, the boxes that you guys work on that, you know, provide air flow to all these spaces. I'm going to say 98%, I'm going to just go out on a limb here. 98% of those terminal units are what they call pressure-independent VAV. What do I mean by that? Well, what I mean by that is that inside that box, there's a flow rate that measures the flow through the box. So you know exactly what the flow rate is through the box. You got a damper, right, that controls the flow rate through the box based on what? Input from the VAV controller, okay? So what that does is the flow rate can change, but the box will always try to control to that set point that it's given for flow. So that's what we call pressure independent. That is, doesn't matter if the pressure gets high on the upstream side, doesn't matter if it gets low. That damper is going to adjust and try to maintain that flow rate independent of pressure. Everybody got that? That's what it does. Okay, it's a pressure independent box. Now on the water side, we do pressure independence a couple different ways. We do it that way, which I just explained. We get a flow meter, we get a valve, remember that closed loop, remember this, is that still on the board here? Yeah, so what you can have, if you want to go back to this we have a valve that works to control flow just like this. That is to say, we measure the flow, right? We go in, we got some control functionality. This actuator is on what? This is actually the control valve itself, right? And we control the flow independent of pressure. That's one way to do it. The other way to do it is we come up with what we call a mechanical force balance device. And what we do then is we control differential pressure. So we keep the differential pressure constant across the valve, and that's another way to be pressure independent, right? So two ways to skin the cat. Okay.
Yeah, we have those on like hydronic heat pumps a lot.
Right. You can put a pressure independent valve on a. Now here's where the confusion comes in. I want to really clear this up because there's a misconception in the industry about pressure independence. Somebody will say, "Yeah, I got one of those. I got a pressure independent valve. I got the automatic balancing valve. Man, it's pressure independent." Well, yeah, at one point. And what's that point? The design point, right? If you reach your design flow through that coil, your automatic balancing valve, yes, will be pressure independent above that point because it will limit that flow to that independent of pressure above that point. But that is not a pressure independent valve. What I'm talking about, the pressure independent valve, is that it will control the flow independent of pressure throughout the throttling range, right? If you got a 10 GPM valve, it's going to be a pressure independent all the way from 0 GPM up to 10 GPM. You see what I mean? So when you're actually controlling the valve in the control range, it's going to be pressure independent there, not at design. So that's just one. If everybody tells you, yeah, we got pressure independent valves, well, check, because you may have basically just a balancing valve with a regular old pressure independent valve. Two different things. So let's just, I don't want to put too much math on you here, but so here's our formula that we used before, right? Well, essentially when we take the pressure out of it, so now we have no differential pressure that we're going to like design to. The CV is sort of equal to the flow rate, so it makes it all really easy now. So what you're going to do now, if you had to pick a valve, say your coil is 10 GPM or 15 GPM, you can go into our catalog and you can pick a valve that flows at design flow of 15 GPM, or you can adjust it to that, okay? That's the way you pick them. So that's the easy button, okay, as far as picking. But from your guys' standpoint, you're going to be going out to systems that are either pressure dependent or pressure independent. That's what you're going to see. And I guess I'll venture to say in the next 5 to 6 years, you're going to see more and more pressure independent installations. And so I'm just trying to give you a little bit of a heads up. Okay. All right. So now we're sort of going through all the design type stuff, but now we're going to talk about something that you guys definitely deal with. It's called pipe size. So this is something you might see in the field where, there's a really ridiculous. You can see a really ridiculous situation. You might see a 6-inch line. You know, you got a big air handle, right? You got a 6-inch run out. Does everybody know what I mean by run outs? It's the piping that goes off the main and goes to the air handling unit. You see a 6-inch pipe, and then you get this 2-inch valve installed in the 6-inch pipe. Yeah, it happens. It's not really the best thing, and maybe somebody wasn't thinking. Really, what I think is the guy who did the 6-inch runout probably wasn't right? Because the 2-inch valve, here's one thing that mechanical contractors, not necessarily you guys, but I mean designers, I get these calls probably once or twice a year where somebody calls me and says, hey, John, we need a control valve. Okay, great. For a quote. What's the flow rate? What's the design flow rate? I don't know. It's a 3-inch line. So in a lot of cases, people say, well, I just need a 3-inch valve. Well, no. If it's a control valve, if it's controlling the water, trying to throttle the water, it ain't necessarily 3 inches, right? In fact, what I would say, if you go out and look at valves in the industry, if it's a control valve that's actually trying to control, remember, to throttle the water, it's probably going to be smaller than the pipe, and it could be as small as 2 line sizes below the pipe, right? Because with a control valve, what do you think we're trying to achieve?
Something less than full flow.
Well, no, full flow is whatever the coil wants. What we're trying to do is we're trying to do what we're trying to establish valve authority, okay? So the valve authority is the ability of the valve to control that flow across whatever range that it's given to control. In order to do that, it's got to drop pressure if it's a pressure-dependent valve. Well, actually, it's got to drop pressure in any of it. But when we size those valves, we want to drop pressure. So if you don't want to drop, if you just have a 2-position valve, just open and shut, right? You don't really care what that pressure is. In fact, you don't care. You could minimize the pressure, like no pressure drop, right? So what mechanical designers do is if it's just an isolation valve, like a boiler or a chiller, it's whatever the line size is, right? If it's a 5-inch line, it's a 5-inch valve. Because we don't care about the pressure drop, right? If it's just 2-position. But if you're going to proportionally control it, or if you can use floating point control or something like that, then we got to think about the pressure drop. Okay, does that make sense? Think about it in terms of that valve has to be able to throttle that flow, so it's got to drop pressure in order to do it. That's the way it works, physics-wise. That's the way it works. Okay. So this pipe size consideration is, all right, you size it, but you got to have some concern about, well, okay, if I have this big difference between my runout sizing and my valve size, under certain conditions, that CV that we talked about, you calculate, okay, I think I got this kind of CV. Well, what happens is, physically, you get a big-ass pipe, it throttles down to a smaller valve. What happens is, you don't get as much flow through that valve. That is, it's sort of like a traffic jam, like the fluid it inhibits the flow through the valve, and you don't get the CV you think it is. So here's an example of what I'm talking about. I don't know if you guys can see this, it's in your book, but I just want to show you real quickly. So we got this, can you guys read that, or most of you young guys read it? Okay, so it's a B230. It's a 1¼ inch valve. And the CV, if you look in the book, is 19, okay? All right, well, if you took that valve and if you installed it in a 2½ inch pipe, which would be double the size, right? It would be double size in a pipe. Your CV is like 17.9. Well, you say, well, that's not bad. That's pretty good, right? It's a little bit of reduction, not a big deal. But look at, I don't know let's see if we got it here. No, I want to show you this. This one probably illustrates the situation better. Here's a B260. This is a 2-way valve. It's a characterized control valve. The normal CV is 16 for a 1/2 inch pipe, right? If you put it in a 1-inch pipe, what's the CV? 7. That's a big difference, right? So what would you be doing? If you thought you needed a CV of 16, but you really got 7, you've now undersized that valve, right? You've undersized it based on what you thought you got. Now you have an undersized valve. Now you're going to drop a whole bunch more pressure, and maybe you're not going to be able to get the coil to work, right? So everybody follow me on that? So when you have, this is called a geometry correction. We put this table in our catalog for just this purpose, right? If you're going to pick a valve, you can go and check and see if the geometry correction is something that is applicable. It's not applicable in all cases, but sometimes it is. So this is another consideration that we use when we talk about selection of valves. The next big, I guess we said consideration is leakage class. So this has to do with the valve itself, like the way that it, if it's under operating conditions and you close it, how much leakage goes through the valve, right? How much does it leak? Well, we got classes from 1 to 6. Most control valves start right here. Like 1 and 2 are sort of like, yeah, whatever. But 3 through 6 is where most of our valves sit. And you can see here, this is, I think what this is 1/10% of CV. This is 100% of CV, so relatively low. You go all the way down here to class 6, and class 6 is what they call, well, it's nothing, every valve leaks, right? I don't know if you guys know that, but every valve leaks to some extent, right? It's just a matter of how much pressure you put across it. So class 6 is saying they establish a criteria, and you may hear this term, if you haven't already, called bubble tight. Has anybody ever heard that term before? Like bubble tight leakage? Bubble tight leakage is exactly that. What they do is they take the valve, they put air on one side, and they got water on the other, and basically they try to see how many bubbles per minute that the valve will, kick, right? So the fewer bubbles, the more tight it is. That's the way it goes. But anyway, these are the leakage classes. All right. Next one is like pressure ratings. Now I don't know if anybody's ever gotten involved in this, but anybody work in the high-rise buildings downtown?
Yeah. A lot of people.
Yeah. Well, you could get a situation one day where maybe your colleagues up on the hill installed the valves, and you got this valve down in like the basement or in the parking garage, and it's leaking by. They say, wait a minute, hey, this thing's leaking by. What the hell's going on? Somebody's got to go out and check it out. We have what we call body ratings or pressure ratings for valves, and it's based on, this is the general thing for HVAC. We have what we call ANSI. ANSI is just a National American Standards Institute. We have a class, ANSI 125 and 150. This has to do with cast iron stuff, right? And this 250 and 300 actually have to do with malleable iron or ductile iron type fittings and valves and things like that. And then we have actually non-rated ANSI. But here's what I want to get across here. When you have body ratings for the different classes, people think, okay, it's ANSI 125. I can only have 125 psi on that valve, or it's going to leak, or it's not going to hold, right? It's not true. It's a function of temperature, right? So here, if you look here, let's just take 125 here. Here's class 125. This would be like a globe valve or an iron or a bronze cast valve. You can get, if you have chilled water, so if your water is less than 100 degrees, you can go up to 200 psi. It's not 125, right? It's 200 psi. If you go all the way out there in class 300, if you got chilled water, you can have 740 psi before you're going to have some issues, right? So this is where on your high, and the reason I mentioned high rise is because that's where, if you're going to have issues, that's what you'll have. Because say you got like here would be a good example. Say you got a cooling tower on the roof, right? You got a cooling tower on the roof. You're pumping up water. The water's going through the spray tower. If you got a valve in the bottom, in the basement of like a 40-story building, well, when the water goes off, what's going on there? You've got a static head of 40 stories, right? And that can be converted to pressure, right? Because water, the pressure is a function of height, right? So you can have some amount of pressure on that valve in the basement, and it could leak through or not hold the water where you want it to be. So it becomes an issue sometimes. So if you guys ever see leaking valves out there, it could be just that the valve is gone, the packing's gone, or something like that. Or it could be this. It could be that someone put the wrong valve in, and it's not able to maintain the body or the connection rate for the valves. Okay. All right, and then closeout pressure. Well, the closeout pressure, this is, of all the things that happen with valves, this occasionally becomes an issue where someone selects a valve. In fact, I think, I won't mention any names, but one of your competitive the mechanical contractors in town. One of the service guys was on a building and he needed a bypass valve. And the bypass valve was on the 3rd floor of the building, but it was probably like a 40-story building or 35-story building. He puts it in and realizes after he puts it in that, hey, wait a minute, this thing doesn't close off. Well, I try to close the bypass and it doesn't close. Well, this is what it was. His closeout pressure rating was not sufficient at that particular situation to be able to effectively close out the valve. So, good news is, if you ever want to know what the closeout pressure is, it's in this book. The bad news is, you may not find out until you actually start it up that you don't make it. And there's ways to swag it. There's actually ways to figure out what your worst case would be. If you ever get in that situation, call me and we can figure it out. But it occasionally becomes an issue. And like you guys usually get handed over the buildings, right? Like, yeah. All right. So you get the building handed over, you get all the problems, right? So I'm just trying to give you some tools here to say if you find a problem, that it could be something like this. It could be, either a body connection rating is not proper, or you got closeout pressure issues. All that said, I know some of the guys that work on the Hill or in design for McDonnell Miller, and they're capable engineers. But we all fall short of grace sometimes, right? We don't quite make it. All right. Control valve types. Let's see what we got here. Okay, what I'm going to do. Why don't you guys take 5? I'll bring my stuff in, and then we'll set. Let's start about 10 or 5. About 10 or 5. Information on what we call. This is what we call. What we're going to talk about now. I'm just going to talk about valve characteristics. So again, how does this relate to me? I'm talking about you. You can have situations where people put the wrong type of valve in, and what happens is if you get the wrong type of valve in, they may not get the kind of control that you want. So people be bitching about, I can't maintain the temperature, I can't maintain, my discharge air temperature, what the hell is going on? So this is where, sort of like level 2, you go into like, well, okay, what kind of valve do I have in there? So when I talk about valve characteristics, I'm not talking about the way it looks or its color. What I'm talking about is, as you open the valve from 0 to 100%, what does the flow do, right? What's the flow through the valve? I'm sorry, am I blocking you? Okay. So the first one that we deal with, it's called quick opening. And if you look at the way that curve goes, you can see why they call it quick opening, right? Because what happens is, when you start out, if you open that valve like maybe 30% open, something like that, you got almost 100% flow like real quick. And that's good for some applications, but not so good for others, right? So what would this work best for?
On-off control.
Yeah, right, exactly. 2-position, boiler isolation, chiller isolation, heat pump isolation, right? Just water on, water off. What it wouldn't be good for is what? Trying to modulate, exactly. Trying to get that, look how steep that curve is, right? You move that valve just a little bit, you got a huge change in flow. That's really hard to control. So yeah. So 2-position control, quick opening goes together. Here's the second one. So the second one is, and these are major types, linear. So linear means that the relationship between the opening of the valve and the flow through the valve in percent is basically 1-to-1, right? So you open the valve half open, you get about half the flow through the valve. So what kind of application do you think that would work for?
Modulating.
What's that?
Or modulating.
Sort of, yeah. So I know what you're going, and this is one of the reasons we did this. Think about the applications like for water. What kind of valve would you want where if you open the valve half open, you want half the flow of the water through it?
Or coil or hot water valve.
I'm going to say no, but I'm going to explain that in about 5 minutes. Okay, so I'll give you the answer. If you have a 3-way valve that's like doing bypass control or something like that, like a mixing valve, right? Then you want your bypass port. Now, not your control port, but your bypass port, because you remember a 3-way valve has three ports, right? One of them's common. Your bypass port, you want it to be doing this. You want to have the water basically flow. As you open that port more and more, you want about half the water to go through it. Okay, but hold on to this thought because you guys, I know what you guys are thinking, but I want to explain to you why that is not the answer ultimately. Okay, this third one here is called equal percentage. Now, I don't care about the math. There's some math on this, but what I want to show you guys, look at this curve. So you look at it and you go, okay. And then I tell you, I say, well, for almost all of your hydronic coils, like heating coils and cooling coils that you have out in your buildings, almost all of those valves, the control ports, are equal percentage. And you go, no way. You're telling me now, so you're going to tell me, John, that if I open my valve like 30% open, I'm only going to have like what, 8% of the flow through it? And then even if I open it up to like 70%, I'm still only getting like 35% of the flow through it. How does that work, right? What's going on? Well, here's what's going on. There's another thing to consider here, okay? So we start out and say, okay, there's the control valve characteristic, right? And when you're looking, these are actually two plots that slammed onto the same graph. So the blue line is the signal from the valve or the opening of the valve, right? 0 to 100%. And then on this axis is going to be the flow in water through the valve, right? And that's that one there. What do you think this one is?
Your BTUs or your heat.
It's the coil, right? Because remember, what are we controlling? We're controlling flow through the coil. Right? And why do we put water through the coil? To get heat transfer, right? You either want to get a chilled water coil or a heating water coil. It doesn't really matter in this case, but with the coil characteristic, what happens is now we have on this horizontal axis, we've got flow rate, right, in water flow rate in gallons per minute. But on this axis, as Seth said, we got heat transfer, BTUs per hour. That's what we're doing. So if you look at those two curves, and we do this for purpose because these are idealized curves, we call it the footfall, right? You got the equal percentage curve on the bottom. You got this coil characteristic curve on the top. And so here's the deal. From a control standpoint, here's what we want to do. We want to use the valve characteristic to offset the nonlinearity of the coil, and where the rubber meets the road is right here in the middle. Here's why you guys thought that linear characteristic would work for water flow for coils, is because you were thinking about water flow, right? We want the heat flow to be linear, right? We want that heat flow that goes in and out of that coil to be linear. Does that make sense? Not the water flow, but the heat flow. So that's why this characteristic looks so weird. You say, no way. But it all works out. This is why we make equal percentage valves. And if you understand this, you may understand more than most engineers under 3 years of experience, because they may not totally get this, but this is why we specify equal percentage valves. All right, so applications of control valves. This is, I guess this is just sort of like eye candy. You guys know this. We use control valves on all kinds of terminal units, right? VAV reheats, fan coil units, unit heaters. Have anybody gotten here into radiant systems, like radiant heating and cooling?
Radiators.
Chill beams? Well, yeah, radiators, but I'm talking now, like the new radiants now.
Radiant floor.
Radiant floor? Yeah, radiant floor is a form of radiant heating. But now what they're doing now in these fancy buildings, particularly in Seattle and other, I'm not going to get political here, but in other places, they're using what they call radiant beams. They're called chilled beams. You guys heard that term before?
Google.
Yep. Google's got them. Nike's got them.
Got them right down here. The federal government's got them right down
That's
here.
right. So what they are is, just to explain to you what they are if you haven't seen them before, They sort of look like air. They sort of look like these lights, right? Except instead of the lights, you got this sort of like panel. And what that is, it's actually water. It's chilled water and heating water running through coils right into space, right?
Does it actually work?
It does work, but you got to design it very carefully. And one of the things, what do you think the main thing you got to look out for?
Dew point.
Right, dew point, right? So what happens is, the water, the heating water is a lower temperature than you would expect, right? You might think, okay, I have heating water at 160. Well, maybe that heating water is at 130 or 125. And the chilled water, which is the more important issue, right? The chilled water is not 45 degrees coming out of the chiller. What is it? It's more like about 55 or 60. So that what happens is you raise that temperature of the chilled water. You don't want condensing conditions. And then what you do is, on that beam itself, you've got a condensation sensor. So if it hits dew point on that pipe, you know it, right? And you automatically make adjustments. But one of the reasons they do it is that what they can do is they can make warmer chilled water and cooler hot water, right? So you save energy on that. You save the actual electrical energy on that. Plus, and this is more from the architectural standpoint. Now, if you guys don't deal with architects very much, but as a mechanical engineer, I spent many years with them. And it's all about space and light, right? It's all about, we want this grand, we want this 12-foot ceiling, even though your floors only go to 14 feet. We want a 12.5-foot ceiling. We want light everywhere. Well, I'm sorry, if you want a mechanical system, you're going to have to give up some space, right? So what happens is, if you do the chill beams, they don't need as much space above the ceiling. So they can get, you get smaller ductwork in. All you really need to do, if you have a chilled beam, if you design it right, the only air you need to provide to the space is the air for ventilation, right? So you can breathe, right? Minimum and outside air. And then also you need a little bit of air for what we call the latent load, which is there's two types of heating load, and one's called sensible, one's called latent. So you cut down on your fan, you cut down on the ductwork, all's right with the world. The architect gets his 12.5-foot ceiling, and all's good. So that's why they do it. And you'll see what they call radiant beams, which look like this. And then they have these other things that you call radiant sails. And what they are, they're just suspended. They're like these beams that are suspended from the overhead. And I guess they're architecturally cool, but they're coming, and you guys will be maintaining them probably in a couple of years. So that's the yeah. Well, from a valve manufacturer standpoint, we don't mind them, right? They're although I'll show you guys a valve here in a minute, or about an hour or so. It's called a 6-way valve. It's meant specifically for radiant heating and cooling systems. And it's a little bit, you guys never heard of a 6-way valve before. If you're in this class before, you did. But if you haven't been in the class before, you probably never heard of it. All right, so air handling units, all this stuff. We have valves for this, right? Chilled water, hot water, steam. We have valves for the plant. And everybody knows what I mean by plant, right? What's plant mean? When I say plant, what am I talking about? Got to speak louder.
Like chiller plant or your boiler plant or.
Yeah, but what is it? When I say plant, what equipment am I referring to, or what am I referring to? I'm referring to that. I'm referring to the machinery that converts the energy, right? So a chiller's got like a motor, and it basically produces the energy that the distribution system puts all over the place, right? So when you talk about the plant, you're talking about the heart of the system, right? The chiller or the boiler, that kind of thing. Okay. So we have heat exchangers too, which can be considered part of the plant. Like, has anybody worked on what they call a water side economizer? Somebody's laughing. What's that?
Never work on that.
They never work? Is that what you're saying?
So we never work on that.
You never work? You don't? Okay. Well, are you laughing or are you?
No.
Yeah. Well, so what they do is they just save energy because you can use the tower water to actually as a heat exchanger. You can run through a heat exchanger. All right. So what I'm going to do now, this is, if you want to follow along in your book, I think we've got a workbook. We've got some diagrams. I think we do. Yeah. But what I'm going to do now, we're not on the diagrams yet. We're actually just going to talk about different types of valves and sort of how they work. And then we'll get into actually the actual, what we call services of it. So if you have a two-way, well, you guys have heard the term CCV, right? Or has anybody heard that term before? That's our reserved word for characterized control valve. Those are these little ball valves that you're probably used to seeing, and I'll break one out here in a minute. So what happens is here, if you've got the, I'm sorry. Okay. So here we're looking at a cutaway, right? So we're looking at the top of the valve. So what happens here is it's counterclockwise to open, right? And clockwise to close, right? Remember I told you clockwise to close? That's what's going on. So if you rotate counterclockwise, you open, and you rotate clockwise to close. Fairly typical for a two-way valve. Now here's what I meant by, if you guys remember I was talking about a glow valve, this is a picture of a little glow valve, like a little screwed glow valve. So you can see, it's not real evident here, but actually these are actually flat sides, but that's what they call a globe style valve. So here's what it looks like, just the valve itself. Remember the stem, right? It's a linear valve. The action goes up and down. Well, on a linear valve, a linear glow valve, the conventional wisdom is, or the conventional setup, is that if the stem goes up, it's going to open the valve. Okay? So maybe if you don't have any water flow, you can actually determine whether the valve is open or closed. You can pull the stem up, it's going to be open, and then it's stem down to close. And that's conventional. If you look in, so if you look inside that glow valve, this is what it looks like. This is what they call the plug. And then you got the seat where the plug goes on, and you got the stem, which is connected to the plug, and that's what goes up and down. I'm not going through these. So here's I think if you're following on your workbook, you can follow along here in terms of the diagrams that we have. I'm starting on page 32, I guess, in the workbook. I have a little bit of a problem with this diagram, and I guess I lost the fight on this presentation on whether or not we would include it. But two-way valve in supply piping. Okay, let me ask you a question if you guys can remember. How many control valves have you ever seen in the supply piping tool coil?
Too many.
In supply?
Yeah.
Really?
It shouldn't be, but.
Are they two-position valves, or are they proportionally controlled?
Well, if it's when they put them in wrong.
Well, I'm not sure if they put them in wrong, but the thing is, it's like, yeah, we normally don't do that, right? I mean, where are they normally? They're normally on this side, right? They're normally on the return side. Now, I'm going to indulge my colleagues here and say, okay, if you have two-position control for a two-way valve, you would put it in this way. You would have your, actually, this actually should be reversed, but I'm not going to ignore that. So you put it in there. You can shut off the flow to the coil. All right, good. We're done with that. But here's normally what happens, right? And this is what we normally do on most terminal coils, right? It's on the return side. Now, one thing that I'm gonna probably beat my shoe on the table on throughout this presentation, at least for the next couple hours, is that know what's going on here. And this, for our characterized control valves, it's going to be really important. This A port that's on all of our valves, it's called the A port. That's what they call the control port. That's, we call that the control port. Now, on a two-way valve, there's only two ports, right? This is the control port, and this is the common port. Now, why do you think I call this the control port? You're modulating, and that's where that characterizing disc is. Remember, for characterizing the equal percentage characterization? The disc is actually in the A port. So that's where it actually, you characterize the flow like that funny looking curve I saw. That's where it is. On a ball valve, that's where that characterizing disc is. It's in the A port, and it's characterizing flow. On a three-way valve, it's also in the A port. And that'll make a little bit more sense, hopefully. Okay. Now, this is a really important one. And if you remember nothing else about what I said in the next hour, listen carefully to this. This is now what we call a three-way mixing CCV. There are millions of these things out here. You probably have seen them. If you have Belimo valves in your building, you see three-way valves, right, on three-way valve systems. So you either see one of two types of systems. You'll see all three-way valves, right, where all of the coils are three-ways, right? Or what? What's the other?
Mixing.
Sometimes they select them, right? They'll select three-way valves at the end of the line, like say you have some branches going out that way, branches going out that way. They'll select three-way valves throughout the system, and why do they do that?
Keep the loop.
What's that?
Keep the loop up to temperature.
For bypass.
It's not the loop. It's actually for the pump itself. The pump has a minimum flow, and so when the pump is running, even though you have a VFD on it, you may be able to bring it up and down. It's got a minimum flow that you can't go below, or what happens? You go into surge. Yeah, the pump starts surging. Not a good idea. Tends to break stuff when you go into surge. So three-way valves are either like throughout the whole system. That's what we call Stone Age technology, like 70s technology. Or more likely what you see today is you'll see two-way valves in most of the building, and you'll see selected coils that have three-way valves, and that's to maintain that minimum pump flow. But anyway, here's what I want to get across here. This is a cutaway view of the characterized control valve that's right there. Notice here that it's a cutaway. There's 3 ports in it, right? Call it a T configuration, whatever you want to call it. Let me do this now in case we lose it later. I can emphasize it later, but I want to try to get it across now. This is a 3-way valve. This is that 3-way CCV. And you're going to see a bunch of these in your lifetime if you stay in service. If you look in the top of this, I'm going to pass this around, you can see it. If you look in the top of this stem here, you're going to see slots in the stem. Remember, those slots tell you where these ports are. So you could take the actuator off and say, okay, I know where the ports are, right? Here's the most important thing about what I'm seeing here now. I'll give you the scenario. New construction. You guys don't get involved in new construction so much, but it could be just someone's in there. Say they put a new valve in, right? They put a new 3-way valve in. Fitter goes in, puts the valve in. They take the actuator off first, right? Because you want to spin it in with the pipe wrench. So you take the actuator off. Right. Put it in. Then you go, I don't know, and you stick and you stick the actuator back on the valve. Now, if you remembered exactly what it looked like when you pulled it off, in fact, that's what I would recommend. I would recommend, however it came off, put it on exactly the same way. But if you don't, what will happen is the actuator might get out of sync in terms of the way this valve is supposed to operate. There are only 2 acceptable positions, endpoints for this valve as it sits right now, and one of them is this. And what I mean by that, you're going to see the slots where you're going to have one slot here, one slot here, and one slot here, and the B port's going to be down here. This is what we call open A to AB. Okay. The other acceptable position is 90 degrees rotation clockwise, right? So now we're going to close the A to AB port, and now we're going to open the B to AB path, right? Now, there's 2 more positions of this valve, aren't there? Because that thing just spins, right? You could have it, if you rotate another 90 degrees, what do you have? Now you have all 3 ports open. That doesn't work, right? And then the other, yeah. And then the other position is another 90 degrees, where now the A and the B ports are connected, and that also doesn't work, right? Because what happens, if it's a mixing valve, if you have A and B connected, what happens here? It doesn't go back to the pump, right? It doesn't return, right? We had a situation locally here probably about 7 years ago where we had a mechanical contractor put some snow melt in like one of the local schools, or it was like a sidewalk system. They put the valve in wrong, and so what happened when it froze? It froze the coils right in the slab. They were pissed, and they told us that, well, wait a minute, Belimo said I could do this, and I said no, I don't think Belimo said he could do this because we're really well aware of this. So. Anyway, it was a bad scene. But here's what I'm trying to beat this to death a little bit is that be careful with these 3-way valves and make sure that that actuator goes back on the same way that it came off. Because what will happen is I had one of my customers spend almost 5 hours troubleshooting. Because what was happening is they had the valves in wrong. The chiller was tripping off on low flow, right? Because it wasn't getting enough flow back. And they beat their heads against the wall trying to figure out what was going on. And finally someone said, hey, wait a minute, this valve's in the wrong position. It's just you could be a hero one day if you remember that. All right, the mixing glow valve is, well, we're going to go into this a little bit later, but there's two types of three-way valves in terms of service, right? One's called mixing, and what's the other one? Diverting, right? All right, let's just go off the reservation. What's the difference between mixing and diverting? What's that?
2 input, 1 output.
Right, versus 1 input and 2 output, exactly, right. And so one of the common questions I get, and we've saved some bacon for a while, is like, okay, I want a three-way valve. Is it mixing or diverting? I don't know. Okay, well, you got to go check it, right? Now here's where it becomes a real issue. And this I would underline this or remember this or somehow remember this. If you have a globe valve, you must know whether it's mixing or diverting. If it's a ball valve, one valve with the ball valve, like this three-way valve I just showed you here, this can be used for mixing or diverting. The same valve can be used for mixing or diverting. On a globe valve, it cannot. They're two completely different animals. So if you have a globe valve, you must know whether it's mixing or diverting. So you have to go and actually find out, either physically check the piping or whatever, figure out what it's really supposed to do. Because we just had somebody return a valve where he's on site, he calls me up and says, so here's my model number, what do I have? I said, you have a diverting valve. He says, but can't I just use this for mixing? I go, no, you can't, because it doesn't work. So I want to warn you guys about that. So anyway, for a mixing glow valve, we have, again, water's coming in here, the control port, the A port. Now we also have water coming in here, right? This is called the bypass port. Conventionally, and I don't know, we have mostly fitters in here? No? Sort of a mix? Well, I know in the training for the fitters, I'm sure they talk about these different ports, or maybe they don't, but this is the control port, this is the bypass port, and this would be called the common port. That's typical, okay? But I want to warn you that don't always assume that A is the control port and B is the bypass port. It does change, but you have to actually go back to this process to figure out what's going on. But in this case, everything's good. Inlet A, inlet B, outlet AB. And if you look at this thing, just to show you the way they design it, the water comes in here, the control port, and it goes over the top of this plug here. Look at the shape of that plug. Looks like this, right? It looks sort of like this. And what does that look like? It looks like that equal percentage curve that I talked about, right? It's sort of got that curve in it. That's how they get the flow to characterize. If you look down here, I don't know if you guys can see it very well, the bottom of the plug has sides like this. So what do you think that is? That's the linear characteristic. So that's why that's specifically made for mixing and nothing else. You guys deal with butterfly valves much? Or no? Some? All right, now on a butterfly valve, this is just sort of general nomenclature. With a three-way mixing valve, first of all, just some nomenclature. If you're looking at a three-way butterfly valve, first thing you basically know about this is that there's no such thing really as a three-way butterfly valve. But what there really is what? Two ways bolted onto a T. That's how you make a three-way butterfly, right? So when we define like how the butterfly valve is set up, we call the master valve, and the master valve is always on the run. Talking about the through path of the T, right? So anytime whatever valve is on the run across through the valve, it's called the master valve, and this is called the slave. The reason we do that, now if you look over there, you can see, well, wait a minute, John, okay, one's a master, one's a slave, but it's got two actuators and one's on each valve. So this is just more of a convention because as the valves get bigger, you guys probably have seen them. Eventually, one of the valves gets the main actuator, right? You get those big industrial actuators. The industrial actuator typically goes on the master, right? And that's why we call it the master, because this is mechanical linkage, right? So we're going to be driving there. Now back to, remember we talked about master slave thing on the air side? What did I say about that? we need a special type of actuator. It's called an MFT, a programmable actuator. Well, these are MFTs, right? Because they're mechanically linked, right? Yeah. So if you see a butterfly valve with two actuators on it, those are going to be those programmable MFT actuators, and they need to be. You can't replace them with just a plain vanilla actuator. Okay. All right. And a diverting CCV, this is just that same valve I just showed you here. Here, I'll pass it around so you can see it and talk about it. The diverting CCV, it's the same valve, only now what's happening is, now the flow is coming in the common port, and it's either going to go to here, or it's going to divert, and it's going to go there. Again, same valve, though, not a different valve. This is what I talked about. I stole a bit of thunder here. Here, I'm showing you, when you guys go around, you can see it, the slot markings or the stem markings that show you where those ports are. That's pretty important to remember. Now, a diverting globe valve, remember I said with globe valves, you can't use a diverting valve for a mixing valve and vice versa. One of the reasons is, if you look over there on the far right there, look at the plug. The plug's completely different, right? Remember the mixing plug was like this? The diverting plug is sort of like a barrel. And actually that plug is actually hollow. So the water can actually come up through this port and actually go through the plug and go out this side. And then the other part of actually when the plug lifts up, the water can go that way. That's why you can't use a diverting valve for a mixing valve and vice versa. But note this. This is a really important note if you're dealing with globe valves. What's the common port here? B, right? B. So it comes in here. It goes that way. It goes that way. Here's the key for field stuff. If you're looking at a valve, it's a globe valve, and you don't know whether it's mixing or diverting. The way that you can determine, if you know that this is the inlet port, that is going to be the common port, because in a diverting valve, diverting globe valve, the common port is always opposite the stem, because that's the physics of how that thing works. It has to work where the water comes in and goes that way or that way. So that's one way to know. If you're absolutely sure that this is the common inlet port, then it's a diverting valve. If you know the flow goes that way and that way, that definitely is there. And don't pay attention to AB or AB, because it could be different. It could be different nomenclature. Now an L series valve. Now this is another type of three-way valve, right? But look, it's not a T now. What is it? We call it an L. Right? So now the ball is cut in a right angle. Again, this is something, remember, these are used for switching. We don't use these kind of valves for proportional three-way control. And it actually sort of has to do with the physics. Because if you notice here, we got the L here, right? Now, as we rotate this valve, this is going to get smaller and smaller, and it doesn't, this particular geometric situation doesn't work well for throttling. But it's fine for switching, right? But you can switch it. Does everybody know what I mean by switching? Like, say you got like a 4-pipe system, and the hot water comes in and the cold water comes in, and you want to switch between hot and cold. This is the kind of valve that you use. They're actually a little bit less expensive in some cases. But you do not want to use this type of valve, what we call proportional control of a coil. You only want to use it if you want to switch, streams, right? Through a bypass or something like that. Now again, look, port B is common, right? And it comes in, and it goes either that way or it goes that way. This is one of the things where, as men, we're inclined not to read the instructions. But when you got people putting stuff in for the first time, it's always good to read the stuff that comes with the valve, because it'll give you this kind of information. So, we actually had a situation downtown about 2 years ago where the new installation guys went through 40 coil installations before they figured out they were putting them in wrong, because nobody read the instructions. So, the diverting butterfly valve, same setup really, right? Only the flow is going the other way, right? The flow is now coming into the valve. It's either going through the master or it's being diverted to the slave. Okay. Went through that. So now what we're going to do, if you guys want to follow along, see where I'm at here. I guess I'm on page 34 if you're in the workbook. So here is what we call mixing service for a three-way valve. And all's right with the world here, right? Because we know most of those valves are on the return side, right? In almost every coil that most of the coils you guys go through. Have you guys ever seen three-way valves on the supply side? For a coil? It's not real common around here, but it does the same thing.
It'd be a mixing.
It'd be a diverting. If it's on, here's the key. If you find the valve, if the valve is on the supply side and it's a three-way valve, if it's piped correctly, it's a diverting valve, right? Because what it's going to do is divert valve water around the coil. With the mixing valve, as we see here, you've got water coming through here. This is a heating coil in this case. You've got a bypass, takes the supply from the bypass. The water's through the coil, comes back here and mixes with the supply water and goes back. This does capacity control, right? Because you can control the amount of water that goes through the coil. That's a mixing application. If it's diverting, if you find the three-way valve is on the supply side of the coil, then it's a diverting valve. But it does the same thing, really, right? It really does the same thing in terms of capacity control. It's still controlling the water flow through the coil, except now you're diverting the water around the coil rather than getting it on the backside. I want to show you something here, and I'll emphasize it when we go to the catalog. But in both of these cases, the A port is always closest to the coil that it controls. Remember that, write it in stone, write it on your forehead, whatever you want to do. But this is important because you can find valves that were installed wrong. For instance, someone might say, hey, I don't have enough room to put it in that way. So what I'm going to do is I'm going to put the B port there. It doesn't work. It doesn't work well. Let's put it that way. So if you remember that the A port should always be connected closest to the coil, I don't think you'll ever get it wrong for both a characterized control valve and a glow valve. So diverting CCV, same thing here, right? We still have the A port closest to the coil, but it's on the other side. Doesn't matter. For three-way valves, for the three-way characterized control valves, these guys right here, this is absolutely imperative. You have to put it in the way that we show it, and I'll show you the page in the catalog. You should go just burn it into your memory that it's got to be, A port's got to be closest to the coil. Now, less common is where we have a situation where we're using a diverting valve, an L valve, right? Remember, this is an L valve, L series valve, and we're doing two-position control. We're either going to bring the water through the coil, or we're going to bypass it around the coil. Again, that's two-position. That's not throttling. These applications that I just showed you here, these would be used for proportional control or floating point, somewhere where you're modulating the water through the coil. But on this one, this is going to be a switching or a two-position application. Yeah. Okay. Same thing here. It's no difference.
That's when you know that.
No. All right, now we get into the crazy stuff. Has everybody ever seen a six-way valve yet? Have you ever seen one other than in this class? Okay. There's only one application for these right now. I mean, the main application for these valves is going to be those beams. If you guys ever run across them, they're going to be like. So what it is, here's what it looks like. Basically, you've got heating water coming into one side of the valve. You got cooling water coming into the other side of the valve. And these two ports here are the common ports that go out to the beam. So here's sort of just an overview of things that you could see out there with regard to these beams that I'm talking about. You could see this. And if you see this, what you've got here is everybody knows what I mean by a four-pipe system, right? So you got two heating, supply and return, two cooling, supply and return. The water comes in. They actually don't have the right line work. It's actually reversed, but I'll just explain it to you. The water comes in to a switching valve on the supply side. So the supply side comes in, this switches between hot and cold, right, through the beam. When it comes back out, one of these valves controls proportionally controls the heating water, one controls the cooling water. So what you got there is you got 3 valves, right? You got 7 piping connections, right? 1, 2, 3, 4, 5, 6, 7. And you have 3 points of control for the control guy, okay? That's one scenario. The Cadillac deal is this one, which isn't done as much anymore. Now what you have there is you've got 2 switching valves or 2 on-off valves, and then you have 2 proportionally controlled valves. So you're controlling the water through the beam like a coil that way. So now you got 8 piping connections, 4 valves, and 4 control connections. I don't know if you guys see where I'm going here. So you got this, you got this. Both of these are equivalent to that. 1 6-way valve, 1 control connection, 6 piping connections. So it's more of an installation thing. You guys don't get involved in that, but in terms of when they do the new construction, this is one of the considerations that they have. And actually, we got more on that later, but that's the 6-way valve. All right. Well, I don't have a internet connection. I don't really need one. What I'm going to do now is go through this section, and I actually think we may be almost done. So I know you guys are disappointed at that. But, let's go through. Let's go through. All right. So some of this stuff is going to be new to you guys, and what I'd like to do is I want to introduce you guys to some of the stuff that we've got going that's new. You guys aren't going to see this like immediately, but you are. I mean, if I'm doing my job right, you are going to see it, right? Because things are going to start happening. You're going to start installing these things. And it'll give you a little bit of heads up on your competition. The first thing, this first valve that I'm talking about, we call it an energy valve. So I'm not going to read all this stuff in here, but what this thing is, I put it in the context of stuff that I think you guys have seen. Does everybody know what a BTU meter is? In fact, we were just talking about BTUs per hour at the break, right? So a BTU meter does what? It measures the heat transfer rate of, whatever device, like it could measure like heat transfer through a coil or through a heat exchanger, right? We measure that in BTUs per hour in the United States. This valve, and I actually have one I can pass around to show you, believe it or not. I don't have the flange one because I'm getting weak and old, but what it is, it's a control valve, right? It's a pressure independent control valve. Remember I showed you about those kind of things? It's a pressure independent control valve. So here's what I got here. In this case, here's a flow meter. That's an actual flow meter. Here's the valve. This is a closed loop flow control device, just like this, right? Remember I showed you this diagram here? It works just like that. It measures the flow, and it controls the flow to a set point. So remember that analog output we talked about? That analog output goes to the valve, and that valve interprets it as a flow set point, just like at the VAV box. Does the same thing, okay? Now, in addition to that, you see these temperature sensors here? You got one sensor here, and you got one sensor here. Well, where do you think they go? The supply and return of the coil, right? Or the heat exchanger, or whatever device you're controlling. So, we did this during the break. Here's the equation, right? If you want to know what the heat transfer rate is through that coil, you take 500, that's just a conversion factor. You take the flow rate through that coil, and you take the temperature difference across that coil, and that'll give you the BTUs per hour. And you can convert that to tons if you like. Here's what I want to show you about, this is why this valve is a big deal, is that for any given rate here, if the flow rate goes up, what happens to the temperature difference? It's got to go down, right? Because it's got to work out, right? If the flow rate goes up, the temperature difference goes up. Well, why is that even why would I even talk about that? Say again?
Less efficient.
Right. Well, let's go global. For any given coil, what happens, and this is actually a real thing, they call it low delta T. And if you stay in the industry long enough, that'll come out into your understanding. What it is, it's where, through whatever reason, the coils could get dirty, They could get fouled on the water side, on the air side, for whatever reason. To get your design flow or to get your heat transfer rate, you have to increase the water that goes out to that coil. So what are the implications of that? You got to pump more water from your system, right? You're spending more horsepower on your pump, right? Your pump has to go pump more water, and so therefore, you have to pump more water. So the delta T goes down. That's not good. Why? You're less efficient, right? Just like you said, you're less efficient. You're not. What you want to do for any coil that's out there, you want to give it just enough water so it gets the heat transfer rate you want, and you want to maximize that delta T. You want to make that delta T as big as you can get for any given point in the coil. So what this valve does in a nutshell, it not only, what it will do, it's not only like a control valve and a BTU meter, it's actually a device that takes that data. It actually measures the flow rate, it measures the temperature, and it stores it right on the valve.
How are you guys measuring? Thermal dispersion? Is it a wheel? How you doing it?
No, two methods right now. For the smaller valves that we have, we use ultrasonic. So we call it transit time. I don't know if you're familiar with that. What we do is we propagate sound with the flow and against the flow, and the difference in those times is extrapolated to the flow rate through the valve. The bigger valves right now, we have a magnetic flow meter. I don't know if you're familiar with a magnetic flow meter. They use them a lot in industry. What they do there is they set up a magnetic field across the flow, and when a conductive fluid like water goes through that field, it generates a voltage proportional to the amount of, they call it flux, that goes through the valve. And if you know the size of the pipe, you know remember that Q equals VA? Remember this thing here? Same equation. You can figure out the flow rate if you know the velocity, if you know the area. So that's what they basically do. They measure the flow, and again, this thing works just like a VAV box. It measures the flow and controls the flow. But the cool thing about it from an owner standpoint is if they're trying to save energy, this valve will document the heat transfer rate of that coil. Remember that coil curve I showed you? That thing right there? It can draw that, right? It can plot it. It can take all of the different instantaneous heat transfer rates. You can look at it on an Excel spreadsheet if you want. You can dump the data right out of this thing into an Excel spreadsheet. Let me show you that.
Tenant sub-billing too.
Well, it's funny you should say that, is that what's going on now,
Yeah.
there's this whole thing in the United States about this thing called revenue grade, right? So if you're going to bill somebody, you got to make sure it's like revenue grade. So you get into this whole big morass. Like in Europe, well, I don't want to get political about the Europeans, but they're way ahead of us on this thing, right? They got regulations for like when you get up in the morning. But the one thing they do have, they have a metering standard, right? If you're going to meter and you're going to bill somebody for chilled water or something like that, you got to have a certain amount of requirements and all that kind of stuff. Anyway, I'll pass this around so you guys can see it. This is our littlest energy valve. So in this case, what we got is we got two NPT connections for the pipe because we want to make sure that well is good, so you don't have to put a weld let in. You know, you can just basically screw these into the pipe. And then here's the flow meter. There's the valve. And if you want to dump the data out of the valve, you got this little Cat5 connection. You can hook it up to your PC. You can dump it right out. It actually stores 12 months worth of data. Yeah, 12 months, 13 months. I'm sorry, 13 months.
Could you hook a bunch of them up to like a front end system?
I'm sorry.
Could you hook like a whole series of them like to a front end system and monitor all of them in real time? Right?
All the coils?
Yeah. All those valves.
Yes.
Set the bill.
I forgot the punchline. This is a BACnet device.
Oh, okay.
So all that data is available over BACnet. So if you have BACnet MSTP or BACnet over Internet Protocol, it's available via BACnet. Or it's available, just dump it into your computer.
What's that thing cost?
Huh? Well, it costs less than a control valve and a flow meter.
Yeah. 5,000? 1,500?
It depends. You can look it up in your book. You can look up in your catalog. I don't keep that stuff in my head.
Yeah.
But it's more expensive than a normal control valve.
Yeah. I mean, it seems like you could pay for itself pretty quick.
Exactly. Exactly. No, you're right, and we actually have a spreadsheet that will help you calculate that if you want to try to do it. All right, so that's the energy valve. That's sort of like our what do you want to call our flagship valve product. One thing though, and this is, you guys don't have to deal with this, but installation would have to deal with it. Because it's a flow meter, you got to have 5 pipe diameters of straight pipe upstream of that meter, right? Because you want to make sure that you've got the right, the flow profile has to be right. So that causes some problems as far as, retrofitting and things like that. But it works out pretty well if you account for it in the pipe. All right, so then an EPIV, we call this electronic pressure independent valve. This is the basis of the energy valve, right? We took this valve and made it an energy valve. So it's really the same basic thing, except this does not have recording capabilities. This is just a regular old pressure independent valve, right? You don't have any ability to store data on this. It just does its pressure independent thing. And, we actually make, just as a side, this is our ANSI 250 EPIV. What we basically did is took this meter here and we stuck a glow valve on it because so many people were bitching at us that we didn't have an ANSI 250 valve. We said, okay, we'll make one. So that's what we did. We put one together. This is the one that you guys will probably see the most of, or you'll see them first. Let me show you. So remember I said there was 2 ways for pressure independence? This is mechanical pressure independent. What I just showed you was electronic pressure independent. I'm going to pass this around. You can see how this thing works. This is actually, what this is like a spring force balance mechanism. You got like a plunger here with a spring and like a shaft, and you got a diaphragm here in this chamber. So you got the high side is on the top, the low side is on the bottom, or the downstream side. The water goes through here. It tends to push this plunger down. The water goes through this valve. This is just a regular old CCV, like you guys know. The downstream pressure actually goes through this little tube right here and comes up on the underside of this diaphragm. So what happens is that thing just throttles back and forth. And what it's trying to do, just maintain that differential pressure constant across that valve. That's all it's trying to do. A little less sophisticated than the electronic one, but it still does it. It's still, and actually most of the, if you don't see our valves, we have many competitors now that have mechanical pressure independent valves. That's the way it works. This is an example of one with a non-spring return actuator on it. And what this is a flow, it's actually a calibrated orifice, so if the balancer wanted to check the flow rate through it, he can measure across these taps and go to a chart and confirm the flow. So that's mechanical pressure independent. All right, the baby. Hope that I got it. Hope that I brought some to it. Oh man, I hope I got it. Oh yeah. So I don't know if you guys have an appreciation for what this is. Look at the size of that thing. That's a 1/2 inch, what we call zone type. So we make it. This was actually developed a couple years ago. We released it about 2 years ago. You guys probably know that one of the installations we made this for. You know those like radiators are on the perimeter of the buildings, right? And you got like these little tiny spaces that they go in, and you can't fit normal control valves in. This thing will probably fit in a lot of good spaces. One of the things about this, so that's how you take the actuator off. It's like a pop top, sort of like a pop top. It goes on like that. Now, one thing that, and this is one you guys might not get involved in, but we try to make it less expensive. Remember I talked about the CD? The CD of the valve, and design all that. You set the CD of this valve by changing this stop. So this comes like, if you open this thing up all the way, it's got one CD. If you bring it down to like level 1, it's going to be like some CD. So you can set that thing in the field. So that, I mean, that's an advantage in some cases where you say, hey man, I'm dropping too much pressure. I can open up the valve and get a lower CD and change my pressure. Vacuum touch valve control. So the other thing about this thing from an electrical point of view, because we have electrical installers here, this is a 2-position non-spring return valve. Just guess, what do you think the VA would be on this? I'm talking about the actual load, like your transformer load. What do you think it would be?
5.
5 VA? Lower.
Lower, like 0.2.
Higher.
0.5.
Huh?
About 0.5.
Little higher.
Okay.
0.6. 0.6 VA, which is like nothing. It's like nothing. So you got an 80 VA transformer, you put a lot of these on here. So that's one of the reasons we developed it. We said, it's a relatively energy saving device, and and I don't know if you guys have ever seen our actual old zone valve, our little pop tops. We designed them actually to get rid of those. So we're going to get, those are our valves. So this is actually our valve. So we're going to be putting these in there. So we make, just going on, we make a pressure independent version of that zone type. And it looks like this. I won't pass it around, but it basically works the same way as the PICCV that I just showed you. All right, 6-way valve. Oh. Hey guys, we're trying to get done. 6-way valve. So here it is, right? You've seen one in the flesh. Now we only make these in non-spring return actuation, but just so you can say you've seen one, I'm going to pass it around. Let me show you. I think we got a thing on how it works here. I guess we don't. But what happens here is, just to show you how it works, is it's only got a 90-degree stroke, right? It's 90 degrees total. So what happens is you start out with basically the heating side. You got 30 degrees for the heating, 30 degrees stroke for the heating, 30 degrees deadband, and then 30 degrees for the cooling. So with one control signal, you can control both the heating and cooling to the coil, and like I say, you get away with just one control connection. So it's actually it's a potential labor saving device. All right, CCD. I already passed around the 3-way CCD. These are probably most of what you're going to see out there. We make them in like we call MPT, screwed. We do make some larger ones. Again, these are probably most of what you're seeing out there now. But we're gonna. I think that zone type thing that we passed around might work into the market. So you'll see those more and more as we go. So I want to. We'll go back to a little bit of the design stuff here. This is a 3-way CCV. Remember I talked about that characterizing, the characterizing of the valve? Back in 1998, when we got into the valve business, the things that were being used to control flow were like a glow valve. They were using something like this. Back in 1995, this is what you put on your VAV reheats. It would be either a 2-way or a 3-way glow valve. This is an expensive machine. It's twice the cost of these. So when we came into the market, we came in with this characterized control valve. What we did is we said, okay, we'll take a ball valve, we'll make this characterizing disc, we can characterize the flow to make it an equal percentage valve, and we can do it for half the cost. So we did that in 1998, and now everybody has one, right? Because imitation is the best form of flattery. Siemens has one, Johnson has one. But we were the original people that came up with this idea of using a ball valve to actually control a terminal coil. And we do it with this disc. This is what I'm just showing you what it looks like here. If you have the valve all the way closed and you rotate it counterclockwise, you can see more and more of the opening occurs. And this is sort of what happens to the flow. So that's that equal percentage curve that I told you about, and that's how we get it. You guys deal with steam much? No, not so much? A little bit, right? We actually make a valve for steam, for low pressure steam, 15 psi or less. It's called an HTCCV, high temperature valve. It's a little bit different. Actually, instead of a characterizing disc, we sort of got this like, I'm going to call it like a cone-shaped device for characterizing the flow. And we use it also for water, but not as much. Mostly these things would be used on, if you guys work on humidifiers, yeah, occasionally like in hospitals. You can use this for a humidifier. You can use it for a steam coil, like a steam heating coil. We don't have as many of those. Do we have many steam heating coils left on this side of the mountains?
VA has a lot of them.
That's right, VA. That's right, VA.
Swedish has some.
Yeah, they have humidifiers too in Swedish too. So. Yeah, so you might see them on those types of museums. Now these are less common, but I'll show you. I think I have a picture one here. This first one is an industrial ball valve. So you probably haven't seen many of these. This is a pretty skilled valve, man. It's made by Apollo, and mostly what you're doing with these are it can be two-position control. You can use it for steam. But there's something I wanted to bring up. If you guys are ever involved in replacing valves on what we call atmospheric systems. So what I mean by that is, say you got a makeup water tank. So you got a, you know what I mean by a makeup water tank, right? It's makeup for like the chiller or the boiler. So you might be dumping water into that tank, right? You just got maybe you got a 50 PSI supply, and you're opening up that valve. It's just dumping water into an open tank. Well, that valve that opens and shuts, it's got 50 PSI on the upstream side, and what does it have on the downstream side? 0 gauge, right? You got 50 PSI gauge, and you got 0 gauge. All right. There's only so many valves. There's valves that are suited for that purpose, because most of the valves I've showed you so far, they're meant to be in closed systems, right? With wet, they're going to be wet on both sides, right? So you're going to have water on the upstream side, water on the downstream side. This valve here, the ball valve, this thing can take what we call open-end service, right? Where you can actually have it connected to atmosphere, and you're not going to blow out the valve or damage the valve. If you get into that kind of situation, be careful on the type of valve you choose, because if you want to use a characterized control valve, right, like that little thing I passed around, that's going to work for a while, but eventually it won't work. It's not meant for that kind of service. So, and then this one here, the B3L, this is a switching valve, right? Remember that's that L-type valve that I showed you? And you make one of those for switching. The V-ball, you guys have probably never seen one of these, but I will show it to you. It's from a mechanical engineering perspective, it's actually, well, which one did I, oh, that's just a phone here. This is actually this is an industrial grade valve. So if you guys ever get involved in like high pressure steam applications, what? It's a pretty good thing. Yeah, it is. Look at that. Yeah, it is. And we make it for like high pressure steam applications and things like that. Or this is one application that you guys might get into. Have you guys ever seen like in a mechanical room where they don't have enough room, so they start moving the valves like this way? They got them going sideways. Well, if you use a glow valve, just imagine, where's my glow valve here? Imagine this is a flange glow valve, right? So you're going to orient that thing at 90 degrees. So what do you think is going to happen if you don't support that? The stem, you're going to have like a mechanical moment on the stem, and you could get this thing to leak, right? If you get that application, if it works out, this thing, it doesn't care, right? You can put that thing at 90 degrees. It's not going anywhere, right? Because it's a ball valve, and this is a really substantial stem. So that's why I mentioned. I don't know if you guys want to, yeah, just for the experience. Yeah. And we make them. We make the little ones, and we make the big ones too. We make them up to 6 inches. This thing's going away. I'm not even going to talk about it. This is an old zone valve that we had for many years. Made by Calepi. We're going to get rid of it. All right. Almost done, guys. We're going to get out of here. We're going to get out of here relatively early. So. All right, so how many people have dealt with butterfly valves? Maybe you guys deal with that much, or like on the service side, or no? Not really. Well, just for the record here, we make like 3 different types. We make what we call like rubber seat valves, which are like probably most of what you guys will see out there. We call them resilient seat valves. We do make a valve just in case you ever get involved. We actually source Vic valves, right? Victolic valves, which are like groove joint valves. So we do have a line of those. We actually get them from Victolic, and we put our actuators on them. And then we make what I call the high performance valves, which are, they call them hard seat or Teflon seat. And those things cost an arm and a leg. And you usually don't use them unless you have to because they're very expensive. But, we do make them also. We also now make flow meters. Now, we didn't have that until about 2 years ago. So, I don't know, you guys probably aren't seeing them, but I think your colleagues on the new construction side, more and more people, especially in Seattle, they're monitoring their chilled water flow, they're monitoring their heating water flow. The overarching government is coming down and saying you can only use so much energy for your building. No, this stuff's all coming, guys. It's
Are those revenue grade?
what's that?
Are they revenue grade?
They are not revenue grade, but they will be. We're working. The United States hasn't figured this out yet. They haven't figured it out yet. And I'll tell you a story. This is a true story. In Hawaii, we used to charge. We did a design for Ala Moana Mall. They were charging people chilled water on those funky little turbine meters. They're using funky little turbine meters. They were charging people on flow rate. Yeah. So in HVAC, we sort of like hit things with a shotgun. But now what's going to happen is people are going to get more and more involved in. Yeah.
So one of the things that we're doing on retrofits is putting flow meters on the discharge of cooling towers for deduct meters.
Yeah. How large a meters are you talking about?
2-inch.
We've got them. Should look at them.
But they got to be revenue grade so that they can deduct it from their utility bill.
Yeah.
And they gotta have the scanners on them too, so they can drive by and not get out of their fucking car.
Yeah. You just wait the little thing.
Just out the window. Just a heads up.
That's a typical utility for them, right?
That's exactly right.
It's a typical utility for them. It used to be. Do you guys remember? I'm young enough. I'm old enough to remember like cute meter maids. They used to get out of their car and walk over and read the meter. Yeah, none of that anymore. No more cute meter maids. Yeah. Anyway, no, that's true. So they're making you do SCADA. They're making you do like SCADA systems, or like what do? They just look at it, or what do they do?
Batteries,
Badger makes them?
Badger makes one, yeah. But we set them up anywhere in the building, and they can just sit in their car down a 60-story building.
Wow.
Just hit the scanner and they'll do the incoming and deduct meter both at the same time.
But it's interesting you say Badger has them?
Yeah, Badger, I'm just working on one right now.
Well, we originally, when we got our feet in the water on flow meters, we, for about a year, we sourced the Badger meters. As you know, we said we were going to sell them. And one thing that came out of that, because I was talking with the guy who was like the sensor guy, and he said to me, and I'll say what he said to me, and I'll say it in English, but he says these things are not very accurate. But yet they're revenue grade, right? So that's what I get a little jaded on this, right? Our ultrasonic flow meter is probably plus or minus 2% of reading. How much more accurate do you want than that, right? I don't know. We're going to have to fight this fight as far as if we get in the flow meter business, but yeah, right now the answer is no. But we are going to have, you guys, I guess I'll let you guys know, this doesn't mean a lot to you guys, but it's a big deal for us. In April, we're actually coming out with sensors now, which is a big deal, because we've always been valves and actuators, right? So now we're going to have a full line of HVAC sensors, including flow meter, right? So now we're going to get into the sensor business. And we do have an option on our sensors that if you want to have them traceable to NIST, now that's that revenue, or now that's the agency that says, hey man, this thing's calibrated. We're going to have an NIST option. So I think, to answer your question, we may be able to have a NIST option for our flow meter where you could say, okay, it's calibrated according to NIST. What do you want? Because revenue grade right now in the United States, it's a nebulous term. You know what I think it means? I used to work for Future
How much
Power.
you pay to the
It
government?
means you pay the money
Right,
to
no,
the agency.
that's right, it's pay to play,
that puts
right?
the rubber stamp on it.
Well, I used to work for Future Power, right? And the way I understand revenue grade now is, well, I don't know about Badger, but yeah, the utility bought it. So, you know, it's revenue grade. But I don't know, that we don't really have a standard. I don't think we have a standard. I think it's just like, well, if you can bullshit your way and say it's revenue grade, or I don't know what the criteria is. But we're gonna find out for sure.
You pay the money, I'm sure.
Pay the money. Well, the other thing in Europe, I'll tell you, in Europe, they're crazy. Well, it's not crazy, but this is what's coming here. If you have a revenue grade meter, you need to calibrate it every 3 years or 4 years or something like that. So you're going to need to have an extra one to plug in while you send that one back to get calibrated. So you're going to be like doing like a, can I say Chinese fire drill? You know, you're going to be doing like you're going to be doing that kind of thing with your equipment so that you can keep it in check. All right. Hey guys, it's been a lot of fun. I'm going to let you off the hook on the last exercise. So I know I went through a lot of stuff pretty fast, but let me go get you my cards and then.
Hang on now.
Huh? What? I'm always going to have a prize.
A little love here. Visibility, don't take a minute.
Wait, just leave it here.
Sean gets the